So we finished with the different types of reactions last time. And today we're going to chat about the concept of oxidation and reduction, which is the type of the reactions in which two compounds or chemicals exchange the electrons. So a lot of reactions, biochemical reactions in the human organism are oxidation and reduction reactions. For instance, the basic reactions that extract energy from food are the oxidation and reduction reactions. Okay. So the example of oxidation and reduction reaction that we unfortunately have to deal with quite regularly is rusting of iron. Iron, when it is exposed to oxygen, eventually, although slowly, forms iron 3 oxide, and that is rust. So what essentially happens in oxidation and reduction reaction? Here you have two compounds, A and B. Compound A, okay, loses its electron, giving it to compound B. So compound A is considered to be oxidized. So that's the basis of a mnemonic rule, oil rig. Oxidation is a loss of electrons. You see? Here, oxidation is loss. Compound B here that gains electrons is considered to be reduced. So reduction is a gain of electrons. So you see in the end, compound A is reduced. It does not have an electron. And compound B is considered, so A is oxidized and compound B is reduced. It gains electron. So far, does that make sense? So again, when compound is oxidized, it loses the electron. When compound is reduced, it gains the electron. For instance, the green color of the Statue of Liberty, as well as green patina on any bronze statue, is the product of the oxidation of copper. Copper is oxidized by oxygen, which is reduced, and the final product is copper 2 oxide. So a really good example of oxidation and reduction reaction, which is basically an exchange of electrons, can occur if you will take a solution of copper sulfate. Remember when we worked during the lab 9, 10, and 11, we had this blue salt that we made solutions of. That was copper sulfate. So if you make a solution of copper sulfate, which is going to have a blue color, and you will stick a zinc, I don't know, piece of zinc into this solution and leave it there for a while. What's going to happen is copper that exists in the form of a positively charged ion will exchange electrons with the zinc. Zinc will lose electrons. You see this reaction on top here? I'm going to enlarge it for a second. Okay. Here, zinc will lose electrons. And the reaction under it, right here, copper will gain electrons. When copper gains 2 electrons, it goes from the positively charged ion, copper 2+, to a neutral copper, the metallic copper, Does that make sense? Simultaneously, an atom of zinc that lost 2 electrons becomes the cation in the solution. So what will happen after a while, when you pull that piece of zinc out of the copper sulfate solution, you will see that the zinc piece is covered with copper. So zinc got oxidized, turned into positive cations, and went into the solution, while copper got reduced, became metallic copper, and was left on the surface of that zinc piece. Does that make sense? How is that important in the biochemistry, in the reactions in the human body? So, first of all, I want to write down a very simple chemical equation, which is a glucose plus oxygen. The products of these two, of this reaction, I'm sorry, I hear the music. Is that somebody's? Can you please turn it off? Thank you. So the products of this reaction is carbon dioxide and water. So essentially in this reaction, the molecule of glucose gets oxidized. It loses the electrons to oxygen, producing water and carbon dioxide. That's an example of how oxidation and reduction play a role in deriving the energy for the body function. So basically, when we eat carbohydrates, they get oxidized in the reaction similar to that, producing enormous amount of energy. Does that make sense to you? Now, one of the, not a problems, but kind of, an obstacles to carrying out the oxidation and reduction reactions in the human body is that they involve pretty complicated molecules. Does that make sense to you? Like glucose is, pretty complex molecule, 6 carbons, 12 hydrogens, 6 oxygens. Nothing like this, where you have zinc and copper, and that's it. So these molecules, like oxygen and glucose, cannot exchange electrons directly. They have to go through a series of intermediate reactions. And essentially, the electrons are carried from glucose to oxygen by so-called electron carriers, like the molecule of coenzyme FAD. FAD acquires 2 hydrogen ions and 2 electrons and becomes reduced. Does that make sense? FAD acquires 2 electrons. Electrons are negatively charged. Does that make sense? 2 hydrogen ions that are positively charged to balance out the charges. And that produces the reduced form of coenzyme. The form is FADH2. This form can carry electrons around, right, and deliver them to a next step, and the next reaction, and the next reaction. Essentially, if you think about the oxidation and reduction in the living cell, in the living organism, the whole idea is to move electrons, practically physically move electrons, from molecule A to molecule B in many, many steps. Like taking a ride. Electrons are taking a ride from one part of the cell to another. Does that make sense? In simple reactions, like the one that we saw here, copper and zinc, electrons take a walk from one atom to another. They very close, these atoms. Does that make sense? In the cell, molecules can be very distant from each other. So electrons have to take a taxi, take a Uber, you know, and that FAD-FADH2 pair is a Uber. FAD is an empty car that doesn't carry any electrons. Does that make sense? FADH2 is a loaded car, the car with the passengers, that carries electrons around and delivers it to wherever they are supposed to go. Does that make sense? So, in some cases, in many cases, in bioorganic chemistry, in biological chemistry, in many biochemical reactions, not only electrons are transferred, but hydrogens are transferred as well. For instance, when a molecule of methanol or methyl alcohol is oxidized, it loses 2 electrons and 2 hydrogen atoms. These hydrogen atoms then can be used in the process of respiration. It's not the point. Formaldehyde, this molecule right here, can be further oxidized into formic acid by adding oxygen. And then formic acid can be further oxidized by adding oxygen into carbon dioxide. So we usually say this: if you speak to a biologist, a pure biologist, they will tell you that oxidation and reduction is about loss of hydrogen or addition of oxygen. Does that make sense? So oxidation is either loss of hydrogen or addition of oxygen. If you talk to a chemist will tell you oxidation and reduction is an exchange of electrons. Oxidation is when a molecule loses electrons. Reduction is when a molecule gains electrons. Does that make sense? Now, why we take the methanol example? Methanol is a type of alcohol that is extremely toxic to humans. The products of methanol metabolism, formaldehyde and formic acid, are pretty toxic. The symptoms of methanol poisoning are blindness and eventually death. The toxic dose, so basically about 50 milliliters, approximately 2 fluid ounces of methanol, almost guaranteed to give you blindness, and probably 4 to 5 fluid ounces of methanol, that's almost guaranteed to kill you. Okay, it's a pretty common cause of poisoning when people, get the wrong alcohol to make, a drink, a legal drink. So, to kind of summarize the concept of oxidation and reduction. So, oxidation is when a compound loses electrons or gets oxygens added or loses hydrogens. And compound is reduced when it gains electrons or loses oxygen or gains hydrogen. Are we clear in terms of what oxidation and reduction is? You must know these definitions, you must be able to say what they are.
So can you make an example about reduction, that what situation we can see and understand what is reduction?
These two...
The oxidation, you make an example like a copper, yeah, that's oxidation, am I right? That when the copper turns green because the oxidation because of the oxygen?
I'm just waiting for the end of the answer, question. So if that's all,
Yeah.
oxidation and reduction always happen together.
Oh.
One cannot happen without another. If you pay somebody, somebody earns money.
Oh.
You know,
Okay.
you can't
So
just, you
a
can't just,
reaction
let me finish. You can't just pay somebody without losing money. Does that make sense?
Okay.
And somebody cannot gain money without other person, you know, kind of losing them. So oxidation cannot happen without reduction and vice versa. When copper is oxidized, oxygen is reduced. Copper cannot just lose electrons. I mean, you technically can lose money. Nobody will ever find them. But if one compound loses electrons, another compound will gain them.
Mm.
Does that make sense?
Yes.
So one cannot happen without another.
Okay.
Now, what we need to know when we write down the equations for chemical reactions is one fundamental law, which is the law of conservation of mass. This law indicates that matter cannot be created or destroyed, meaning that the mass of reactants, total mass of all reactants, equals to a total mass of all products. Am I clear? Okay? So, for instance, in this example, the total mass of iron plus total mass of sulfur after they reacted will be equal to a total mass of the product iron sulfide, iron 3 sulfide. Does that make sense? Nothing is created, nothing is destroyed. If you had 2 pounds total mass of reactants, you're going to have 2 pounds total mass of products. So we can look at this reaction and we can say, okay, what if we take 2 moles of iron, right? Because that's the balanced equation right there. And 3 moles of sulfur. And we heat them up. And when they combine, they will produce 1 mole of iron 3 sulfide. Does that make sense? Remember, moles are pounds. They numbers. They aren't mass or volume. They just numbers. Do you understand what I'm trying to say? So, what is the mass of 2 moles of iron? Well, iron is 56, I can tell you. About 56 grams per mole. So it's going to be 112. Okay. The total mass of 3 moles of sulfur is about 96. I'm doing very quick and dirty calculations. Okay. So 2 atoms of iron will still have the mass of 112. 3 atoms of sulfur will still have the mass of 96. So the mass of 1 mole of iron 3 sulfide will be 208. Does that make sense? So now this are the conversion factors that you write from that reaction. So basically, what these conversion factors tell you, and I'm going to go slow over it, so if you don't understand what I'm saying, if you have any confusion about that, please let me know. But basically, this conversion factor between iron and sulfur tells you that in this particular reaction, 2 moles of iron interact with 3 moles of sulfur. Does that make sense? Now, these conversion factors tell you that if you take 2 moles of iron, then out of these 2 moles of iron you can get 1 mole of iron 3 sulfide.
Why?
Because, it's a great question, because you have 2 moles of iron, right? How many moles of iron do you get in iron sulfide? 2. But all these 2 moles of iron are packed in 1 mole of iron sulfide. Let me rephrase it, completely rephrase it. Forget about the moles. Forget about the moles. Totally forget. You have 2 atoms of iron. Follow the equation there. You have 3 atoms of sulfur. Do you follow? Look at the reaction. Okay? Erase the whole thing. So here, 2 atoms of iron. The number 2 refers to 2 atoms. You with me? You have 3 atoms of sulfur. You with me? How many molecules of iron sulfide you get by combining 2 atoms of iron and 3 atoms of sulfur? How many molecules, huh? Just 1. Does that make sense? So 2, 3, and 1. Now multiply the number of atoms and molecules by the Avogadro number, 6.02 by 10 to the power of 23. So if you multiply 2 atoms of iron by this number, how many moles of iron are you going to get? Avogadro number is the mole. If you 2 moles. Does that make sense? If you multiply 3 atoms of sulfur by Avogadro's number, how many moles of sulfur are you going to get? 3. If you multiply 1 molecule of iron 3 sulfide by Avogadro's number, how many moles of iron sulfide are you going to get? 1. Okay, forget about this. Forget about this. Look, what I noticed, again, chemistry is very visual science. The problem is that you look at the numbers. Don't look at the numbers. Think about particles. So, apples, sorry, that is grossly misspelled. Whatever. It's fine. Oranges. Apples and oranges. And this is your bag of fruits. Okay? So you take 2 apples, and 2 apples, 3 oranges. Put them in 1 bag.
Yeah. That part.
Okay, hold on. Does that make sense?
Yes.
Now, if you take 4 apples, and I cannot show you 6 oranges, how many bags are you going to get?
1.
No, 2. Because 2 apples and 3 oranges go in 1 bag. Always. Does that make sense? You make a set. You make a set. Does that make sense?
Yeah.
If you take 6 apples and 9 oranges, how many bags are you going to get? 3. If you take 2 moles of oranges, 2 moles of apples, 3 moles of oranges, how many moles of bags are you going to get? 1. Does that make sense? Now, that's a rhetorical question you don't have to answer. Tell me, what's the conceptual difference between apples and iron, or oranges and sulfur, bags and iron 3 sulfide? There is no difference at all. But when you think about apples and oranges, it's easy. You can imagine those fruits. All I ask you, and I ask you like every class, don't think about letters and numbers. Think visually about atoms and molecules, the particles. Does that make sense now? Better? Good.
I mean, See the Fe, the iron and the iron sulfate?
Sulfide.
Yeah,
Yeah.
sulfide. Okay. And then the formula will become on the bottom is a 1 mole of the iron,
Sulfide.
And sulfide, iron 3 and sulfide. But then why on top of it it's only 2 mole of iron? Where
Which one are you talking
sulfide
about?
go?
This
the
one?
Second one.
This
The
one?
second one and the third one.
They mixing.
This one?
Yeah.
Because you have 3 moles of sulfur, and you need 3 moles of sulfur
I know.
to have
But where
3
did
atoms.
iron go? Where did
Because that's a conversion factor between these two. Iron didn't go anywhere. We just don't, like, I mean, it just tells you that in one bag, you have 3 oranges. It doesn't tell you anything about the apples. It's not the purpose. It's not there. It's the conversion factor. Look, it's the conversion factor for sulfur versus iron sulfide. It doesn't involve iron at all. Iron is here. Does that make sense? It's just different conversion factor. You cannot make a conversion factor with 3 different categories. Does that make sense? Okay. Now, why do we care? Why do we care about these conversion factors? Here's the question. How many molecules of iron 3 oxide, how many moles, sorry, of iron 3 oxide can be produced from 6 moles of oxygen? Does that make sense? The question, do you understand the question? So if we take 6 moles of oxygen, how many moles of iron oxide can we make? So if you look, you can calculate, you can check your calculations. I'm going to explain step by step. If you take 3 moles of oxygen, you're going to produce 2 moles of iron oxide. Before we move on, do you understand that? That comes from the equation. Without even looking at these conversion factors, if we take 6 moles of oxygen, how many moles of iron oxide we produce? Hmm?
3?
No. No. Okay. Say again? 4. Look, if 3 oranges go into 2 bags, then 6 oranges, twice as much, will go in 4 bags. Does that make sense? If 3 moles, okay, do you cook?
Yes.
If the recipe tells you to get 3 eggs to make a pie, if you need to make 2 pies, how many eggs are you going to take?
6.
Is there any difference? Not really.
I think it's just the names that it's
No. You have to understand, it's cooking. Chemistry is actually cooking. It's following the recipe. So this recipe tells you that if you take 3 moles of oxygen, you're going to produce 2 moles of iron oxide. Does that make sense?
Okay.
Now, if you take twice as much oxygen, not 3 but 6, how many moles of iron oxide are you going to produce?
4.
Twice as much? Does that make sense? Better? It's all about cooking. That makes sense? Actually, a real story. The dean of one chemical college back in Moscow, in like 70s, he was a very famous guy. The very first exam, like semester final, had only one question. He gave students ingredients, the recipe, and they had to make an omelette. That was it. And if you can make an omelette, you keep going. If you can't, you're out. Like you expelled. Chemistry is cooking. Does that make sense? Now, these mole conversions are important when we need to find the actual mass of the chemicals that are produced in a certain reaction. For instance, when acetylene and oxygen burn in the welding device, we can calculate the exact mass of acetylene that is used to weld a certain amount of metal. Okay? So, let me explain what we're going to be doing here. Imagine that you have a substance A, okay, that interacts with 2 moles of substance B, producing the molecule like this, AB2. Does that make sense? Those are absolutely hypothetical, like some stuff, okay? So, 1 mole, 2 moles, 1 mole. You following me? Write it more. A plus 2B gives you AB2. Now, if you know how many moles actually of substance A you took, say, I'm going to ask you this question now. Imagine that I took 4 moles of substance A. You with me?
Yeah.
4 moles. How many moles of substance B do I need for the reaction? 8. Make sense? Perfect. How many moles of substance AB2? I will have 4. Fantastic. Now, if I know a molar mass for substance A, this one, molar mass, the mass of 1 mole, can I calculate the actual mass of substance A?
Yeah.
Yes. Can I calculate the actual mass of substance B that I need to put on the scale? Yeah. Can I predict how much substance AB, what's going to be the mass of substance AB that I will get?
Yeah.
Excellent. Another question. I don't know anything about the moles. All I know is mass. I know like that I have 100 grams of substance A. Do you follow?
Yeah.
And I know molar mass. Can I find how many moles of substance A I have? If I know total mass, if I know a mass of 1 mole, can I find how many moles I have?
Yeah.
If I know how many moles of substance A I have, can I find how many moles and grams of substance B I need?
Yes.
This is called mass calculations. And they're crucially important. So I always tell that when you start mass calculations, it's really important to write an equation. Give yourself enough space on the paper to write everything down. Are you following me? And then carefully lay out what you know and what you need. Okay? And then I usually suggest, if you know like mass and molar mass, find out moles immediately. It just helps. Okay? So for instance, here we have a reaction between nitrogen gas and hydrogen gas that produces ammonia gas. Does that make sense? So we know that we have 32 grams of nitrogen gas. This is something that we know. What we need to find is the mass of ammonia that can be produced. You follow? Mm-hmm. So first, we want to figure out how we're going to do it, the plan. If we know the mass of nitrogen and the molar mass of nitrogen, can be found how many moles of nitrogen we have? Mm-hmm. Sure. If we know how many moles of nitrogen we have, can we figure out how many moles of ammonia we can produce? Yes, how? Yeah, it's twice as much. Does that make sense? 1 mole of nitrogen will give you 2 moles of ammonia. Does that make sense? And once we know how many moles of ammonia are produced, we can find its mass using its molar mass. So these are the steps. 1 mole of nitrogen is 28.02 grams. Okay? That's the molar mass. So here we have 2 conversion factors. 1 mole of ammonia is 17.04 grams. So we have these 2 conversion factors. And finally, when we look at this reaction, our third set of conversion factors is this, that 1 mole of nitrogen is equivalent to 2 moles of ammonia in this reaction. Does that make sense? We good? So now we are setting up the equation. So first, we need to convert 32 grams of nitrogen into moles of nitrogen. So we use this conversion factor, moles on top, molar mass at the bottom. You with me? Then we need to convert moles of nitrogen into moles of ammonia, so we use mole-mole conversion factor. Okay, nitrogen goes at the bottom because here nitrogen's on top. And finally, we need to convert moles of ammonia into the mass of ammonia. So we use a third conversion factor, the molar mass, to find the mass of ammonia. Now, this is super long, and I would rather do something else. Let me quickly change something. I'm going to end slideshow. Okay, actually, you know what? Sorry about that. Something's wrong with my hands. So, the last portion that we're going to chat about today is the issue of energy and chemical reactions. So, you did some chemical reactions that produce a lot of energy, right? For instance, you burned the magnesium band, okay, and it produced enormous amount of heat. Remember that story? You did it in the lab. So, The idea is that there are two types of the reactions, exothermic and endothermic. In exothermic reactions, energy is released, and in endothermic reactions, energy is required. And we're going to talk about it a little bit more. So, why chemical reactions do occur? How do they occur? Molecules have to physically interact with each other. We call it a collision. Okay. They have to interact with each other while they are in the proper orientation. And in order for the reaction to proceed, that collision must provide sufficient energy, called the energy of activation. So the first example of a chemical reaction is exothermic reaction, which release heat. So in this graph, you can see the energy level on y-axis and the reaction progress on the x-axis. So you can consider the x-axis as the time. Do you follow me so far? So here is total energy of reactants, and here is the total energy of products. I'm going to explain it in the proper chemistry term, and then I will give you an analogy. So you can see that the total energy of reactants, I'm going to call it E1, is much higher than the total energy of the products, E2. E2 here. Okay? So what's going to be the difference between them then? Hold on a second. So the difference, sorry, I have no idea. The difference between E1, the difference between E1 and E2, okay, no, it doesn't work. I'm sorry. The difference between E1 and E2 will be essentially that number, that difference between the energy. That's the heat that is released in the course of the reaction. Is that clear? Now let me explain it in analogy terms. Imagine that you have a stone sitting on the roof of a building. Does it have a potential energy?
Yes.
Is it higher than if that stone would be on the ground?
Yes.
You throw the stone on the ground, is energy released?
Yes.
The kinetic energy. Now, since it's on the roof, you have to lift it first to get it over the railings. Does that make sense? This is called the activation energy. That's the energy that you have to invest in the reaction first to get it going. The simplest example of activation energy, when you burn paper. If you take a sheet of paper, it's not going to burn in the air. Does that make sense? Mm-hmm. You need to invest energy by setting it on fire. And after that, this reaction, will it release energy or take energy in? It will release in the form of heat. Does that make sense? But you need to invest energy in, like, lighten things up. Does that make sense? Mm-hmm. Now, here, in the endothermic reaction, the energy of reactants is lower than the energy of products. Can you see that? So you need to invest this heat for reaction to happen. Does that make sense? You need to spend energy to get your chemical stone from the ground on the roof. And you still have to get over those railings, the activation energy railings. Does that make sense? So the great example of endothermic reaction is the one that we looked at before. Here, this one. Okay? This reaction requires an enormous amount of heat to be invested for it to go forward. This reaction happens at the temperature of about 500 degrees Celsius. Okay? Just to provide enough heat so it can go. Does that make sense? Now, one important term, you probably have heard about it. Have heard the term catalyst? Catalyst is anything that would lower the activation energy. Does that make sense? That will remove those railings. So the reaction will go faster. Are you with me? So I'm going to give an example. Have you heard about the term enzyme before? Enzymes are biological catalysts that speed up the reactions in the cell. And one of the easiest examples of a catalyst that you can actually do at home, like you can see that. So are you familiar with hydrogen peroxide? I guess you are familiar. Typical 3% that you can buy at any pharmacy. Does it have an expiration date? Yeah, it does. Yeah. Hydrogen peroxide, with time, if you just leave it, it will break down into water and oxygen. Does that make sense? The reaction is like this. Okay. Now, that happens over, especially if you keep it closed and in the dark plastic bottle, it'll take years for a complete breakdown. So it happens very, very slowly. Does that make sense? If you have hydrogen peroxide at home, you can do a very, very simple and pretty cool experiment. You can take a glass and pour some hydrogen peroxide into that glass. Then you can take a fresh potato, fresh raw potato, chop it really well. The more you chop it, like the finer, the better, like pretty small pieces. Throw it in hydrogen peroxide, several pieces, and you will see bubbles coming out. That's the enzyme, the biological catalyst that is found in potato, called catalase, which speeds up this reaction. And the bubbles that you see are oxygen. So the reaction will happen in a matter of literally seconds. You will see them right away. Does that make sense? So I want to highlight it for you, kind of, that's the piece of information to cling on to, is that catalysts, including cellular catalysts that we call enzymes, they reduce the activation energy. Does that make sense? Now, that activation energy will determine, as you can imagine, the rate of the reaction. The rate at which either the reactant is used up or the product forms. Does that make sense? So you can actually measure it. For instance, you can measure how much product is produced over a certain period of time. Okay? For instance, you can measure the rate of that reaction that I drew on the board decomposition of hydrogen peroxide. And if you can somehow measure the volume of oxygen that is released, you can say, okay, we've got 1 mole of oxygen released in 5 minutes. Okay? So it's going to be, the rate is going to be 1 mole over 5 minutes, or 0.2 moles per minute. That's the rate. Does that make sense? It can be expressed through different equations. You always write it down. The point is, rate of the chemical reaction is something you can kind of play with. So you can increase it. Okay? When temperature goes up, the rate of chemical reactions, generally speaking, goes up. Why? Molecules start to move faster. They collide more frequently. And since they collide more frequently, remember, collision is something that is necessary for the reaction to occur. The more collisions, the faster the reaction, the more conversions of molecules will happen. Does that make sense? If you will increase the concentration of reactants, the reaction will go faster as well. Which also makes perfect sense, because when you have more reactants, the amount of molecules, the concentration of molecules is higher, which means they will collide more frequently. Does that make sense? Now, this is something that we talked about already, the catalyst, okay, which increases the rate of the reaction by the lowering the activation energy. So, as I mentioned, that railing, so think about this. If you have, I don't know, a 200-pound round boulder sitting on the roof, and you need to throw it down, okay? Although it has an enormous potential energy, and it's energy, releasing process, if you have railings on the roof, you can't lift 200-pound boulder. You just can't. It's physically impossible for you. Does that make sense? So that reaction will never go forward. If you remove the railings, you can push it. You can't lift it, but you can push it. Okay? You still have to invest some energy. Does that make sense? What's important? Generally speaking, catalysts are not used in the reaction, not wasted. So, for instance, that reaction that I showed you here, the reaction of generation of ammonia, along with the heat, requires a catalyst. Catalyst is a metal. It's platinum. Just platinum. So these platinum catalysts are installed at the plant where ammonium is produced, and they install there for years and years and years, and they just stay there. Okay, and they facilitate that reaction. Does that make sense? They don't have to be changed. Platinum doesn't go anywhere. It just stays in that reaction column. So to summarize the factors that increase the reaction rate, that's concentration of reactants, because that provides more chances for molecules to collide. It's increased temperature, which increases the number of collision and also allows more collisions to achieve the energy of activation. And when you add a catalyst, the reaction speeds up because catalyst actually lowers the energy of activation. Does that make sense?
So if you put that catalyst in there in the factory to make the ammonium,
Yes.
you still need the 500 degrees.
Oh yeah, yeah.
So if you didn't have the platinum in there, you'd need a much higher temperature to make that happen.
I don't really know. Yeah, probably so, yeah. You probably would. So basically the idea in the industrial settings, it's all sort of a question of if it's profitable. Because if you use so much energy to produce ammonia, it's going to cost like gold. Nobody's going to buy it. And, it's not. So platinum, and by the way, that's kind of, there's another way how you can convert extremely inert nitrogen into something that is more chemically reactive. You can take nitrogen and oxygen and produce nitrogen oxide. The only problem is that this reaction requires a temperature more than 2000 degrees Celsius, which makes it industrially impossible to carry out. Make sense? So it's just not economically feasible. That's why we use ammonia. Still pretty terrible, but at least makes sense. Okay? So